What specific problem does the new method or algorithm aim to solve?
The new method or algorithm, described in the paper, aims to solve the problem of efficiently generating a large quantity of synthetic data with comparable privacy guarantees to existing methods. Specifically, the algorithm focuses on improving the efficiency and scalability of private prediction methods for generating synthetic text datasets. It addresses the limitations of existing approaches, such as the prohibitive training procedures of private fine-tuning methods and the degradation of privacy guarantees with the volume of data generated in private prediction methods. The algorithm introduces novel algorithmic elements to enhance performance, including leveraging the uncertainty inherent in sampling for privacy protection, clipping and aggregating token logits before sampling, and using an auxiliary token distribution from an LLM to reduce privacy costs. By generating synthetic examples using fixed disjoint subsets of sensitive prompts and incorporating public prompts when possible, the algorithm significantly increases the quantity and quality of synthetic data while maintaining privacy.
How does the proposed method or algorithm work? Illustrate step by step.
The proposed method for generating private synthetic text works by first partitioning the input dataset of sensitive prompts into disjoint batches. Each batch contains a set of prompts that are used to run several large language models, LLMs, inferences in parallel. Each synthetic example is generated one token at a time, with the average of the logit vectors across the inferences defining the distribution from which the next token is randomly selected. Before averaging, the logits are clipped and recentered to ensure privacy. The algorithm also has access to a non-sensitive public prompt and uses it to generate the next token whenever doing so does not significantly change the distribution from which the next token is drawn. The privacy guarantee of the algorithm leverages the inherent randomness of token sampling and reduces privacy cost by using public data to generate a portion of the synthetic data. The algorithm ensures differential privacy by satisfying the var delta differential privacy condition, where var and delta are privacy parameters. The method minimizes privacy cost by only incurring it when selecting tokens from the distribution determined by the average logit vector of sensitive prompts. The algorithm's efficiency is enhanced by generating each synthetic example using a fixed disjoint subset of the input data, allowing for parallel composition and avoiding repeated recomputation of the prefix for each decoding step.
What are the theoretical or practical benefits of using this method?
The theoretical benefits of using the method described in the paper include the preservation of differential privacy while generating synthetic data, leveraging the inherent randomness of token sampling to ensure privacy, and reducing privacy costs by incorporating public data in the generation process. The method also minimizes privacy loss by using a non-sensitive public prompt to generate tokens when it does not significantly alter the distribution. Additionally, the algorithm's privacy guarantee is independent of the number of public output tokens, which is advantageous in maintaining privacy levels. Practically, the method allows for the generation of a large quantity of synthetic data while maintaining quality, enabling rapid prototyping and iteration in applications that require synthetic data. The approach is computationally efficient as it uses a fixed disjoint subset of sensitive prompts for generating each synthetic example, leading to scalability in generating large synthetic corpora. Furthermore, the method can produce thousands of training examples, which is crucial for fine-tuning downstream models. Overall, the method offers significant improvements over prior work in terms of both quantity and quality of synthetic data, making it a valuable tool for various applications requiring differential privacy in synthetic data generation.
How is the method validated or tested?
The method is validated through a series of experiments across different scenarios. In the in-context learning experiments, the synthetic examples are compared against real examples, and the downstream accuracy is reported on various classification and extraction tasks. The experiments show that the synthetic data generated by the method is comparable to real data, even outperforming real data in some cases. In the fine-tuning experiments, the method is used to generate a large quantity of synthetic data for fine-tuning BERT models, and the downstream accuracy on real test examples is reported for different classification tasks. The results demonstrate that the method can generate thousands of synthetic examples at reasonable privacy levels, competing with state-of-the-art private fine-tuning methods. Additionally, experiments in the limited data regime show that the method generates more useful examples for in-context learning compared to other approaches. Finally, in the structured data experiments, the method is evaluated on a JSON generation task, focusing on the rate of well-formed outputs and schema validation. The results show that the method, leveraging the sparse vector technique, provides a lift in performance by avoiding privacy loss on syntactic elements of the data, leading to better generation quantity.
What results were achieved with this new method?
The new private prediction method described in the paper achieved significant improvements over prior work in terms of generating synthetic data. The method was able to produce hundreds of times more synthetic data compared to existing private prediction methods while maintaining a comparable privacy guarantee. Specifically, the method was able to generate thousands of training examples, which is a substantial increase compared to prior methods that only generated a small number, fewer than 10 of examples. In experiments, the method demonstrated the ability to generate between 5K to 200K examples for fine-tuning across various datasets and privacy levels, outperforming previous methods that were limited in the number of examples they could generate. Additionally, the method showed improvements in downstream accuracy for classification tasks, surpassing the performance of existing state-of-the-art private prediction methods. The results also highlighted the method's effectiveness in the limited data regime, where it generated more useful examples for in-context learning compared to other approaches. Overall, the new private prediction method showcased a significant lift in performance and efficiency in generating synthetic data for various machine learning tasks.
What are the limitations or drawbacks of the method?
The limitations or drawbacks of the method described in the paper include the potential compromise between sampling temperature and the well-formedness of outputs, especially when targeting a large number of examples at small epsilon values. This compromise can lead to a decrease in the quality of the generated data. Additionally, the method may require significant noise levels to ensure privacy when using the Gaussian mechanism, which can impact the quality of the synthetic data. Another limitation is the computational expense associated with generating each token using a different random sample of sensitive prompts, as this prevents the use of KV cache accelerated decoding and can limit scalability. Furthermore, the method's reliance on fixed disjoint subsets of sensitive prompts for generating synthetic examples may restrict the flexibility in data generation and could potentially impact the diversity of the synthetic dataset. Lastly, the method's privacy guarantees may degrade with the number of private output tokens, which could affect the overall privacy protection of the generated synthetic data.